In this video, I'm going to show you a bunch of examples of 1D time series signals and 2D images and their power spectra computed by the Fourier transform. I'm not going to go into detail about the math or the mechanisms of the Fourier transform, not until the next section. But I think it's interesting to see visually what signals look like in the time domain and what their corresponding amplitude spectra look like in the frequency domain. That will help you build some intuition, which in turn will help you learn the Fourier transform. And I hope it will also generate some excitement because you'll be really looking forward to understanding everything that I'm going to show you. I'm going to show you these examples in MATLAB. There's going to be a lot of code in MATLAB that I'm not going to explain now, but will become more clear if you follow along in MATLAB with the rest of this course. So if you feel like the code looks difficult and you don't understand it, then don't worry. For now, just try to pay attention to the pictures. By the end of this course, you will be able to understand and adapt this code. Our first example will be a pure sine wave. Here you see the sine wave in the time domain. It goes up and down over time. This is a sine wave at 5 Hertz, meaning that there are 5 cycles in a 1 second period of time. This is the time domain. Here in the frequency domain, you see just an impulse, a spike, at 5 Hertz. And I could change this sine wave from 5 Hertz to, for example, 15 Hertz. You would see that the sine wave is faster now, and the impulse is further to the right, and it's now at 15 Hertz. All the other coefficients are 0. This next example shows a signal which contains multiple components. Just by looking at this signal in the time domain, it's not totally clear exactly how many sine waves are in this signal and what their frequencies are and what their amplitudes are. However, by looking at the same signal in the frequency domain, you can see very clearly and immediately that this signal comprises 3 distinct sine waves at different frequencies and with different amplitudes. This is one of the major advantages of inspecting a signal in the frequency domain compared to the time domain. This example shows pure noise. This is just white noise, so random numbers that are normally distributed with a mean of 0 and a standard deviation of 1. And the power spectrum of noise actually should be totally flat. It's not flat here. That's mainly because we are sampling a limited number of noise points. So if you think there's some patterns in this amplitude spectrum, then rerunning the code and generating new random numbers will show that in fact this really is just a random spectrum. This next signal is something called Brownian noise, which is also sometimes called a random walk, and it's sometimes called pink noise or fractal noise. You can see that it's a little bit smoother, and it has a very large low frequency component relative to the higher frequency components. The next example shows another kind of noise. This is called 1 over f noise. And it's called 1 over f because the amplitude decreases as a function of increasing frequency. And the mathematical function that characterizes this relationship is 1 over f, where f is frequency. Here you see the amplitude spectrum of a square wave. So this is a square wave that takes 1 at some values and 0 at most other values. And it has kind of a funny looking, almost bouncy amplitude spectrum, but many of the frequencies have 0 amplitude. This signal is amplitude modulated. This is similar to how AM radio works, where you have a carrier frequency, which is a pure sine wave, and then the amplitude changes as a function of time. These fluctuations in amplitude can be used to transmit information like an AM radio, but they also are non-stationarities, which have sometimes unpredictable effects on the amplitude spectrum. So I will talk a lot about non-stationarities in a later section. This signal shows frequency modulation. This is similar to how FM radio works. So now you can see the amplitude is the same over time, but the frequency of the sine waves is changing. So sometimes the sine waves are slower and sometimes they're faster. And you can see again that this creates a fairly broad distribution in the frequency domain. In this example, I am simulating broadband noise similar to what I simulated up here, except now I'm applying a narrowband filter to suppress features at all of the frequencies except for the frequencies that are around 10 Hertz in a Gaussian shape. And that produces kind of interesting looking time series as well. All these examples are of one-dimensional time series, and I'm going to spend most of the time in this course talking about one-dimensional time series. However, I do want to show you some images as well, so you get a sense of what a two-dimensional Fourier transform result looks like. This first example is something called a Gabor patch. It's a two-dimensional plane, so it's an image, and it has something that looks like a 2D sine wave, but there's a spatial Gaussian in here as well that makes a kind of nice visual pattern. This is the amplitude spectrum of the image and the phase spectrum of the image. These are quite a bit more difficult to interpret than just the amplitude spectra from the 1D time series that we were looking at previously. The low frequencies are in the middle and higher frequencies go out to the edges. So this is a Gabor patch. Here we have random noise, and random noise looks like random noise, both in the space domain and in the amplitude and in the phase. Here I have a picture. This is a famous picture. Maybe you don't recognize it just yet with the color map, but we can change this to a gray color map. And now you might recognize this is a famous picture of a Playboy model from, I think, the 70s. Her name was Lena. It's used very often to test algorithms for image compression. Here I'm applying a low-pass filter. This is what the original picture looks like. And now I'm applying a low-pass filter by modulating the amplitude spectrum in the frequency domain and then going back into the space domain and reconstructing the modulated amplitude spectrum. The effect of this low-pass spatial filter is to smooth the image. So you see that now it looks much smoother. It's more blurry than it used to be. We can make it even more blurry. And at some point it becomes so blurry that you don't even recognize it as an individual. Conversely, I can also high-pass filter this image. That will filter out all of the low spatial frequencies and allow only the very high spatial frequencies, which corresponds to sharp features in the image. Then what you really notice here is the eyes and the features in the hat and the edges of the image. And in fact, filters like this are used for edge detection in image recognition. And again, I can change the parameter of this high-pass spatial filter. Here is a bit less spatial filtering. Here is even less. And here is even stronger spatial filter. Finally, I'm going to phase scramble this picture. Now what I'm going to do is take the original image, leave the amplitudes untouched, and just scramble the phases randomly. And you can see that that completely destroys the picture. This shows how important the phase spectrum is for the representation of the signal. So these are different random iterations of changing all the phase values in the image. So here I showed a lot of examples of time series and images and their Fourier representations. I hope you're excited now to learn about all the mathematical and implementational details of how the Fourier transform actually works. In the next section, I will start getting into those details.